Okay, let's get started. Welcome to the last lecture of 16A for this semester. There will be a bunch of review sessions throughout next week. There will be normal discussion on Monday, on Tuesday and Thursday during normal lecture time. Your amazing GSIs and UGSIs will be covering review lectures for you. I will be out of town for a bunch of the week because I have to visit Carnegie Mellon, but I will also try to schedule extra office hours sometime next week, as well as hopefully before the final. I will post a schedule to Piazza about all of these things. Okay, so last class we left off at a bit of a cliffhanger, right? We stopped at a point where we thought we had a great technique for sequentially pulling out signal from this combined signal, potentially pulling out these transmissions from a combined signal. And we were on our way to developing this method of orthogonal matching pursuit. And at the beginning of class last time, I talked about these ideas of supervised learning versus unsupervised learning. And I wanted to come back to that a little bit in case I wasn't very clear. So OMP is an interesting algorithm which has elements of both supervised learning and unsupervised learning. Remember, supervised learning is something where you're given a label for a particular data point. Like you're told that this data point represents a cat, this other data point represents a dog, so on and so forth. In OMP, we're given a received signal, right? We're given a Y signal. And so one can think of this also as being some kind of labeling or some kind of data. But the unsupervised aspect of the algorithm is the fact that, well, we don't know exactly which devices are transmitting, and we're able to pull these out one by one without a priori knowing the IDs of the devices. We don't know whether it's your toaster or your fridge or your microwave transmitting, but you can learn this just by looking at the data. And so this aspect of figuring out these IDs is something that is similar to the ideas that you'll think about in unsupervised learning. And if you want to learn much more about this, obviously take 16B next semester, where you will go into much more detail on different kinds of unsupervised methods. In particular, you'll talk about principal components analysis, and singular value decomposition that will help, build up these techniques even more. So just quickly set up what we had last time. Remember, we had 2,000 devices in our home. And these are, your toaster, your fridge, your pen, so on and so forth. And they're all transmitting. And you want to figure out which device is transmitting at a given time. The thing you know is that only a few devices are on at any given time. So we had a notation for all of these. Let's say we have devices that are 1 to all the way up to 2,000. They all are transmitting their codes S1, S2, S2000. This is the code. This is the device ID. And then on top of this, they have some kind of message that they might be transmitting. Alpha 1, Alpha 2, all the way up to Alpha 2000. And what we receive is this vector y, which is equal to Alpha 1 S1 at shift tau 1, plus Alpha 2 S2 at shift tau 2, plus Alpha 2000 S2000 at shift tau 2000. Right? And these taus here I'll add tau 1, tau 2, tau 2000 are my shifts. So we have this, and what we know is that actually only very few of these, maybe like 2 or 3 or 4, are transmitting. So most alpha i's are 0. And this is what we mean by sparse signal, or a sparse unknown. And remember, we can write this in our standard format as a matrix vector equation. So I can write S1 at tau 1 all the way up to S2000 at shift tau 2000 times alpha 1, alpha 2, all the way up to alpha 2000, which is equal to our vector y. And here we have this sparsity, which means that most of these alphas are actually 0. And what we want to figure out is we want to figure out which alphas are non-zero, which means this is equivalent to asking what devices are on. Which ones are transmitting? Is it your toaster or your microwave or your whatever? I don't know. What's another device in your home? Your pen. Which ones of these are non-zero? So you want to figure out the device IDs. If there's 3 or 4 or 5 of them, let's say they're I1, I2, I3, I4. What are the device IDs? Which of these are on? And in addition, you want to figure out for the ones that are on, what are the appropriate tau I1, tau I2, tau I3, tau I4. And then, of course, the alphas corresponding to that. Alpha I2, alpha I3, alpha I4. And remember, we're not writing I1, I2, I3, I4 and just tau 1, tau 2, tau 3, tau 4, because we don't know what I1, I2, I3, I4 are, right? If I told you that I1 was equal to 2, then you would already know that device 2 is transmitting. So I1, I2, I3, I4 are also our unknowns here. This is a bit unfocused. Okay, sorry, this is as focused as it gets. Can I zoom in a little bit? Yeah, okay. So I have a question here. What is the number of equations we have? We have at least 2,000 unknowns in the sense that our traditional x vector here, or what we might call an alpha vector here, is 2,000 long. But how many equations do we actually have? Yeah? The length of the signal, right? So the number of equations is basically here, n is equal to the length of the gold code that you're actually dealing with, right? And so if I wanted to have n equations for n unknowns, this would mean if I have at least 2,000 unknowns, I'm going to have a gold code of at least length 2,000. But a gold code of length 2,000 means that there's a lot of processing overhead, right? We're going to have to do a lot of these cross correlations. And so usually we want to do gold codes that are of much smaller length. And that's what we kind of started doing in our demo, right, last time. So let's go back to here. Oh yeah, this is one of my favorite memes from one of the last semesters. So I think it's pretty great. Just wanted to share it with you guys. More memes that connect to content are highly encouraged. Oh, this doesn't work? Now it works. Yeah. Anyway, exit that. And let's go back to here. So remember, what did we try to do last time, right? Last time, we looked at, well, let's think about a simple setup first. And let's figure out what happens when you have only one transmitter, right? What if you have y equal to alpha 1, s1, tau 1, right? That was the first thing we did. And then, you can't see this. Here. Yeah, this is from last time, right? We said, what happens if y equal to alpha 1 times s1 tau 1? And we tried to figure out how we can deal with just this one situation, right? And so what we did last time, the first thing we tried was we explored what we could do for one signal, right? This was the gold code. Then we explored what these gold codes look like. We explored what their cross correlations look like. And then we found the peak with the maximum cross correlation, which told us which device was actually transmitting. Right? Everyone remember this? Okay. And then we decided to move to this case where there's actually multiple signals, right? So now here, can everyone read this? Again, this is the same demo as last time. And again, reminder, this is involved. There's a lot of notation. There is code. And it's going to be valuable for you to try to follow along. So if in case some variable name isn't clear, something gets confused with notation, feel free to stop me and ask. Because if you miss what a certain notation means, it's really easy to get lost for the rest of the lecture. So, feel free to ask me questions if you can. And if I accidentally start talking about something on a computer, but that's showing, or vice versa, also please help me out by telling me. Okay. So here what we have, again, is this is the length of the signature, or the length of the gold code. And look, we're only having a signature, or a gold code length, of 400. So how many equations do we have? We have 400, right? And the maximum number of users we want to think about is 2,000. And how are we assigning these signatures? We're basically assigning them randomly, right? We're randomly populating plus and minus ones to generate these signatures, right? For example, we showed an example here of what that signature looks like. And then what we said was, well, let's take one of the gold codes. Whoops. And then correlate this gold code at shift 100. First, we'll correlate it with itself, and then we tried correlating it with something else. And what did we get with that? Right? We saw that, well, remember, it's important to see what these plots are. The x-axis here is the shift index. So that means that this is, tau 1, tau, this is the value of tau. And when I correlate code 23 with itself, what shift do we expect to see the most correlation at? We're correlating a shifted version. We have the first signal is basically the shifted version with shift 100. And the second one, we're rotating, right? We're doing all possible shifts. So what shifts is going to match up if the first signal is at shift 100? It's going to match up at shift 100, right? So we see that basically we have very low correlation for all of the shifts except shift 100. And what we're looking at here is a normalized correlation, right? Because we're dividing by the length of the vector. So if we weren't dividing by the length of the vector, the cross correlation we would get would be 400. Right? Because we would get 1 plus 1 plus 1 plus 1 400 times. So we're getting 1 here because this is being divided by 400. Now here in the second plot, we're saying, let's consider the cross correlation of two different gold codes. So 23 and 20, and here what we see is that at all different shifts, your signal is very close to zero. You don't see this peak at all. And in fact, what you receive is, might be some combination of this. But basically, in comparison to the peak here, the correlation here doesn't really affect anything. So then we decided to try and set this up, and we said, okay, well, let's say we have 3 devices transmitting 40, 100, 312. They are transmitting these different alphas, and they have these different shifts. And then we defined actually our Y signal here. This is our signal Y. And then we tried to see what would happen if we can do the correlation, right? And we basically got 3 peaks here. And we got peaks for which 3 devices did we get the peaks? We got them like somewhere, pretty small, close to 10, somewhere around maybe 50, and then something close to above 250. And so which are the devices we're expecting? We're expecting 40, 100, and 312. So this is close to this is close to 40, this is close to 100, and this is like 312, right? You're eyeballing this. So is that clear to everyone? Okay. So you have these 3 peaks that correspond to these 3 devices. And so we can figure out what are the indices for the 3 maxes we find. And we see that the largest index is at shift 100. The second largest one is at shift 40. The largest correlation is for device ID 100. The next one is for device ID 40, and the next one is device ID 312. Is it clear to everyone that this graph has a different x-axis from this graph? Yeah?
So when we have the correlation between one signal, we multiply it by Alex and 8, but that's not exactly the height of the correlation.
Great question. So his question was, we multiplied by alphas 10, 10, and 8. But if you look at the peaks that you're getting here, they're not exactly 10, 10, and 8, right? This one is like slightly less than 10, this is slightly larger than 10, and this is slightly less than 8. And the question is, why is that happening? And that is exactly the question that we're going to explore in the rest of lecture. And this is very connected to the reason that we couldn't actually recover the signal in the case where we had the 4 signals transmitting, the thing we ended with last time. So by the end of the lecture, your question should be answered. Okay, so we decided that, okay, in this case, what we tried was we said, well, we know what the 3 shifts are. If we know what the 3 shifts are, we can set up our matrix because we know what tau 1, tau 2, tau 3 is. We know what the 3 devices are, so we know the 3 S's. We can populate the matrix, and then we can just do least squares to be able to actually figure out what the signal is, right? Because now we have 400 equations, but we have reduced our number of unknowns to 3 by picking out only the 3 transmitting signals that gave us peaks. Is that clear to everyone? Okay, and then you run least squares, and what you get out is exactly 10, 10, and 8. So because we're running least squares here, you're able to recover exactly 10, 10, and 8, whereas what this is plotting is exactly just the inner product. But it'll become more clear as the lecture goes on. Okay, so everyone remember this? We're good from last time? Okay. So then we decided to do a second trial, right? So what is trial 2? So let's say we have, again, the same setup, code length of 400, 2,000 users. We again make the same signatures. Let's say now there's these 4 devices present, 40, 100, 312, and 350. And the signal strengths are now, different orders of magnitude. Order of magnitude is basically how big is alpha? So 110, we say, are different orders of magnitude. 101 are 2 orders of magnitude different. So we have, the different device values, the different alpha values, and then we have these different shifts, which are the taus. So we have the shifts 13, 20, 45, and 34. And then we create this combo signal, right? Which is just adding all of these things up. And then we said, okay, let's see what we get. Let's again plot the max correlation. And what happened here? The big issue was that we didn't see the 4 peaks that we expected to see, right? Even if we had 4 signals. We saw only 1 peak. And why did we see that? Where did that come from? Why did we only see 1 peak? The strength of the signal, right? Basically, what was happening was that this alpha 1 is overpowering all of the other alphas. And that was the only one that popped out. And so the idea that was suggested was, well, if you only have 1 signal that is dominating everything else, see what happens if you can get rid of it. What happens if you somehow can remove that? What do you get? So we figured out, well, what is the device with this max? That's device ID 40. What's the shift? This is at shift 13. And so, we said, well, let's assume that we somehow figured out that the maximum value was 100. Once we do that, what we see is that actually we start seeing these other signals pop out, right? But there was a big thing that happened here, which is we said, well, how do we know what this is, right? We don't know that this is 100. We're just pretending we know. Somehow some genie told us, some magic happened. But we don't actually know this. So we're on the right track, but we want to figure this out a little bit more. And so now we're kind of improving this further. So instead of, just populating this with this 100, what can we do? So this is just running the same code again. I will do it quickly. So here we basically see that what we get is that we have device 40 transmitting at shift 13, and the maximum value of this normalized cross correlation is a little bit above 100, right? It's actually 100.6522. This alpha 1 that I'm plotting here, do you see this? I'm just finding the exact value of this peak. Okay? But we know because we've rigged the example that this is not exactly the value that was being transmitted, right? This is our guess for what it was. And so now, instead of removing this 100 that the genie told us, what we're going to remove from the combo signal is the actual height of the peak, because the height of the peak we can measure. We see this. So we remove that, and let's see what happens. Okay. Stuff starts to pop out, right? Our next peak is actually becoming visible. But remember that, as was pointed out, we're subtracting something that is slightly different from what we expected to get. Okay, so now we see that the next largest peak is showing up, and it's a little bit above 10. It's device ID 100. It's at shift 20. Okay, let's remove that as well. Okay, we get another peak. We have 312 is the device ID, shift 45, and now we get this peak at, approximately 8, but slightly lower. Again, what did we do? We now removed from the combo signal both of the peaks, right? And what were the alphas that we chose? We chose the alphas that were the height of the peak. So we didn't do any magic, no genie work. We just chose these alphas that were the heights of the peaks. Okay, so now if we keep following this pattern, and we remove now this 4th thing, we would expect our 4th signal to pop out. Remember, what were our 4 signals? These were the 4 devices that were present. These were the signal strengths, and these were the shifts. So we would expect to see a peak at 350. But we're not seeing anything. And part of the reason for that is the alpha that is on top of this is so small. And we left off here with basically, trying to figure out, well, what can we do? So, I don't know, maybe and some of you guys had a chance to go back and think about this. Anyone have any great ideas for what we should try and do? Yeah?
Design-wise, keep all the signal strengths greater than the average value of the noise they expect.
That's a great suggestion. His suggestion is saying, well, you've talked about the design principle. You're saying, you get to design the signals. Don't design bad alphas. What is happening here? You chose a bad alpha and now you're complaining. Well, it's your mistake. Don't make that mistake is what he's saying. Choose alphas that are all approximately equal to each other and significantly above the, baseline correlation that you will get due to interference, right? Because we know that cross correlations are not exactly zero, they're close to zero. Our signals are approximately orthogonal, not perfectly orthogonal. Make sure your alphas are significantly above this noise level. That's a great suggestion, and actually in practice, that is what is done. So if you think about CDMA, where gold codes are actually used, one of the things that does happen in cell phone towers actually is that if there's one or two cell phones that are overpowering and they're sending really, really large transmissions, they will actually be told by the cell tower, hey, your transmissions are drowning out everyone else. You should reduce your power. So this is actually something that is done to try and keep all of the alphas approximately similar so that one alpha doesn't drown everything out. But in some cases, there's actually other things that we can do. So any other suggestions? Yeah?
I'm thinking, can we filter the actual devices? So for other ones, the correlation should be similar, but there's one that has one peak out of all of the small numbers. So then we can pick that one out and say you're special, and then try to calculate.
Yeah, the suggestion is to say, can we somehow filter things out? And that's exactly what we're going to try to do. The challenge is that we have to do it slightly intelligently, because the trivial way of filtering just gives us these noisy peaks, right? It's producing these phantom peaks. It's as though these devices, at 40 or 100, are present, but they're not actually there. And so these phantom peaks that we're seeing, you're looking at them and the locations seem kind of familiar, right? They're actually, remember, we have these two signals here at 40 and 100. And remember, when we removed the signal, we didn't actually remove 100 times the signal at 40 and 10 times the signal at 10. We removed 100.65 of the signal, of the first signal, and we removed 10.39 of the second signal. So we actually had a little bit of an error, right? And what is popping up here is that difference of 1. Right? Because there's a little bit of that residue that's left over. There's a little bit of the component in that direction, and that's popping up here. And because that component is so much bigger than this 0.02, it's drowning out that peak. So coming back to the question that was asked of these correlations that we're seeing aren't quite right. Why are they not quite right? It's because we have actually different signals that are slightly bleeding into each other. And so because the correlations that we see, because the gold codes that we have are not exactly orthogonal, they're only approximately orthogonal, sometimes a little bit of a signal from one gold code can show up in another correlation to the gold code. And that's why you're seeing these peaks here, and that's what's causing the problem. Yeah, question?
We don't know how sparse our vector
Great question. If we don't know how sparse our vector is, how do we know when to stop? This also will be answered by the end of lecture. Effectively, what you will do, there's many different ways. You can have an understanding of the ambient noise level. And as soon as your error gets to that kind of ambient noise level, you can start to say, okay, I have enough. If you Another way is to just keep finding things. You don't stop. You just keep going. And then you kind of guess based on how good you're doing. So there's different ways. Again, this is an element of something where you have to make a decision without precisely knowing what the data is saying. So there will be an element of uncertainty always, because at the end of the day, we're trying to do something that we're actually not allowed to do, right? We're trying to say, I'm not going to give you enough equations, but figure out all these unknowns anyway. Yeah?
Is the position of the error peak at the same user ID as the first?
Yes. If you zoom into that, I don't have it set up so that I can zoom in, but it would be exactly at that point.
Do we have two signals that we subtracted out at this point though?
Yes.
Would there be two error peaks if there was a bigger?
So basically one of them was a really small error, which is why we're not seeing that one. So this error was tiny and it's not showing up. This error was larger in comparison. And this error was also larger in comparison. So the larger errors are dominating. That's what's happening. Does that make sense? Okay. Everyone good? Yeah, question? Great question. The question is, in this setup, isn't the signal that we're subtracting bigger than the message that was sent? Isn't 10.3 bigger than 10? Right? Yes, 10.3 is bigger than 10, but remember, we're plotting correlation, so we're plotting the absolute value. Right? Remember, everything's squared, so that's why we are getting positive things. Because negative, even if the correlation is a large negative number, that still means a strong correlation. Okay, all great questions. Good. So now, finally, we're here. So, what are we going to try and do? So, what we're going to see is that we're seeing that there's a little bit of bleeding from these signals into each other. And so what we're going to say is that instead of removing these things one by one by one, let's actually try and project things simultaneously onto our different signals. So let me shift to here for a quick moment. So just to get everyone on the same page, what have we done so far? Thank you. So first, we found the largest peak, which is basically we found an I1 and a tau I1, which is the argmax over I comma tau of y and si tau. Right? So what does argmax mean? Find that variable that maximizes this expression. Find the argument. So I and tau here are arguments or variables. We're searching over all i's and tau's and finding that I, that device and that shift that maximizes this inner product, right? That's what's happening here. Find that largest peak. And then we say, this gives us tau. And then we remove it. And what we said was, let's consider y1 is equal to y inner product with s I1 tau I1. So let's say we found, this gave us an I1 and a tau I1, right? We take those values, we plug them in, and we get this y1 is the component, in a sense, we just say, well, what is the height of the peak? Times the signal, right? And then we said, well, now let's consider what is remaining, which is y minus y1. And then, find the next peak, which is basically I2 comma tau I2, which is argmax over I comma tau of y comma si tau. So basically subtract the peak times the code you found. Thank you. Subtract the peak times the code you found. Take this e. Oh, messed up. This should not be y. This should be e. Take what is left and now find out the next code that matches it the best, right? And now kind of keep going. Right? That's what we did. We basically, every time we found this peak, and then kind of say, now you'll find a y2, which is the second peak. And then remove y2. And then you have, again, your e, let's call this e1, let's call this e2. This is e1, e2 is now, oops, sorry, y minus y1 minus y2. And keep going. Right? That's what, this is, all I'm writing out is exactly what we just discussed. Nothing new happened. I just wanted to write it out formally. But we know that this doesn't work. And we know the reason it doesn't work, right? We know the reason it doesn't work is something that you guys have been asking about and observing and saying, hey, this thing that you're subtracting off doesn't equal the thing that we rigged. Something is weird here, right? This isn't quite what we want to do. So the way we're going to fix that is we're going to use projections, or we're going to actually come back to least squares. And we're going to use the fact that with least squares, we know how to project not just onto one vector, but sets of vectors simultaneously. And so even if there's some overlap between the components, we can simultaneously get what are the best components in each direction. So let us actually try and do that. So we're going to think about an improved second algorithm. So I'll keep this sort of here, but our algorithm 2 that we're going to try now is very similar. The first step is actually exactly the same. Find largest peak. And this is again I comma tau I. Okay? And now, instead of removing from y, just this term, which is the height of the peak times s, times the signal, what we're going to say, remove from y, the component of y that is explained by SI1 at shift tau 1. So I'm going to call this, let's call this matrix A is equal to basically just this column vector. And now, if I wanted to project Y onto the subspace that was spanned by this column S1, what am I going to do? I'm going to use least squares, right? That is what, like least squares, we know there's multiple interpretations of least squares. One is to find the projection of a vector onto another subspace. Another is to figure out the solution to when you have different numbers of equations and unknowns. So when you have an overdetermined system, so you have basically more information than you have variables, you can use this, right? So here, we're thinking about it in the projection interpretation. So we're going to think about Y1 is basically, if I call this A1, I can use this usual formula, A1 transpose A inverse, A1 transpose, times Y, right? So this is the projection of Y onto subspace spanned by A1. So this is what we're going to do. And so if we go back to here, what I'm going to do is instead now of subtracting off alpha 1, alpha 2, alpha 3 separately as these values. So this was alpha 1, our estimate of alpha 1. This was our estimate of alpha 2. This was our estimate of alpha 3. What I'm going to say is let's try and use all of these simultaneously. I'm going to make an A matrix that is all of these three signals and simultaneously subtract it off. So what we have here is the first step of the algorithm. Here we're doing 3 steps in one go, but we're going to come back and complete this algorithm. So what we're going to do here is just, trial and error. We're going to see if we have this idea, does this actually work? Instead of just subtracting off one peak at a time, what if we simultaneously project onto the subspace spanned by all 3 of these things and subtract that off? So I do this, I get this array, and I run this, and what do I get? I basically get, let me print max 4, print shift 4, exactly what I expected. So what just happened here, right? What did we expect to get where did we expect the 4th peak to come? We expected it to come at 350. But what was the issue we were seeing above here? We were seeing that there was a little bit of the components in these other 2 directions along the first 2 signals that were still remaining, right? And what we're seeing is that because we use least squares, we're able to remove all of that component and therefore have this signal, final signal, pop out. And this gives us the final, peak at 350. So now the thing is, how do we actually formalize this and make this into a function, and what do we do? Here we did it in a little bit of an ad hoc way. So now let's go back, and actually I want to define the OMP algorithm to you. So the first step here is basically what we said, is instead of now projecting simultaneously onto all of these, we did like basically a kind of hodgepodge algorithm there, right? We said like, oh, we see these big peaks, let's remove them, let's simultaneously project onto them. Instead of doing that, we're going to do this systematically. So every time, instead of just choosing the maximum value of that correlation, instead of just using the inner product, we're actually going to use the correlation. Sorry, we're not going to use the correlation. I misspoke. We're going to use the projection. That was a verbal typo. Is that we're not going to use the correlation. We're going to use the projection. And remember, the projection is just a normalized version of the correlation. Okay, so we're here. We found the largest peak. And now, instead of, removing this inner product, what we're going to remove is this projection, right? And remember, because this is a vector, what is this equal to? This is basically equal to the inner product of SI1, tau 1, and y divided by the norm squared right? So we have this guy. This coefficient, this is basically equal to this times. Right? Remember, A1 is just this vector. This guy is just this quantity. Because remember, what is A transpose A when A is just a vector? It's just the norm squared, right? And then this A transpose times Y is just this inner product. And this is a scalar and this is a scalar, and so we can move the directions of these around. Right? So instead of this guy, instead of subtracting out this guy, the height of the peak, what we're subtracting out is this normalized version, right? We're dividing by this length, which is giving us the projection as opposed to a scaled version of the projection. Is this difference clear to everyone? Yeah, question. Great question. It might just be that this should be tau I1, sorry. If that was the question that was sponsoring this note. All of these should be tau I1s. This was me not writing properly. So tau 1 is the specific shift of device 1. Tau I1 is the shift of the first device we found. So in that case, the shift of the first device we found was device 100, and we found some different shift for it, right? It wasn't that the first device we found was device 1. So tau 1 would be the shift for device 1. Tau I1 is the shift for the first device we find. Subtle difference. Good question. Thank you for catching that. Okay, other questions? Okay, so we've done this. Now what we're going to do is we're going to come back and say, okay, now let's set our E1 is equal to y minus y1 and find largest peak in E1. So I2, tau I2 is basically argmax of I comma tau E1 Si tau. Okay. And Now what we're going to say is now 4 is where things start to get a little bit different. So far we've been doing something very similar to what we did in the first algorithm. But now we're going to use these squares. We're going to say maybe there's a little bit of signal that is bleeding from these two codes S1 and S2 into each other. We're going to simultaneously remove both components by doing a projection onto the subspace that is spanned by them. So we're going to say remove the component explained by A2, which is equal to Si1 tau I1 in the first column, and then Si2 tau I2 in the second column. And so we're going to write Y2 is equal to A2 transpose A2 transpose A2, A2 transpose Y. And then E2 is now Y minus Y1 minus Y2. Now what is going to happen the third time around? What are we going to do again? We're again going to go back. We're going to find the largest peak, right, between E2 and all of the devices. And we're going to keep going and keep going and keep going until we know either that we have exhausted the number of devices because someone told us there were 3 or 4 or 5 devices, or we're or the magnitude of our vector is super small. Yes, question? Yes, thank you. Least squares formula, good. This is a projection. This should be an inverse, yes. Question? Yeah, question? Other good question. This should not be A2 transpose, this should be A2. Sorry, I was just writing too fast. I think I wrote the transpose here instead of the inverse here. I apologize. Everyone catch that? Yeah? Actually, you're right. We should be doing that. That was another typo. My notes here say the right thing. Okay. We're subtracting the component in both directions. Yes?
So this algorithm will only work when our sparsity level is less than or equal to the length of one of the signals, right?
This algorithm will only work when our sparsity level is less than or equal to the length of one of our signals. Essentially, yes. So this algorithm only works when you have a large signal. The sparsity has to be significantly smaller than that, and it only generally works for fairly large matrices. So basically, it's hard to construct examples that are somewhat small. Like, if you just think about 4 and 5 dimensions, it's hard. But basically, the sparsity level has to be much smaller compared to the signal length. Yeah, you're right. Yep. Wouldn't E2 be E1 minus Y2? Good question. Actually, not quite, because we're thinking, it's a very good question. Here we're thinking about how much of Y can we explain from the signals we've observed so far. So Y is what we're observing, and Y2 is the part that we've explained out. So because we're trying to explain Y, and Y2 is basically an updated version of Y1. But that's a very good question. Yeah. No, for algorithm 1, it was fine. Yeah. For algorithm 1, basically, you're trying to sequentially remove every single signal. So it depends on how Yeah, there, because all you're removing is the peak, you want to remove them one by one. You're not actually doing this simultaneous projection there. Yeah?
Does this hinge on the fact that all the signals are orthogonal to each other and also every solution?
So signals are, this is exactly coming from the fact that the signals are not exactly orthonormal. They're almost orthogonal, but they're not completely orthogonal. That's why they're bleeding into each other. If they're perfectly orthogonal, the first strategy of just removing this, the first algorithm that we did would actually work. If all of the gold codes were perfectly orthogonal to each other. The reason we're doing this is because there's some bleeding. Okay, I'm going to take one last question and then we have to move on. Yeah. Does this algorithm assume you're taking two signals out at once? So in the first iteration of this algorithm, you're taking one signal out. In the second iteration, you're taking two signals out. In the third iteration, you're taking three signals out, so on and so forth. So I'm going to show you another way of thinking about this algorithm, and hopefully that will also get to some of the questions that you've been thinking about. But basically, a good way to think about this algorithm is the following thing. So what we're seeing here is basically, how do we think about this, right? At iteration 0, we haven't found any signal. So we don't have any A matrix. We haven't explained any of Y. All of Y is unexplained. And the measurement we have is Y. But at iteration 1, we found we found the first guy, right? We found S1 tau 1. So we set A1 to be that. Then we remove that component. We find what is the component in that direction. We remove that. So that is what is unexplained. This is the part that is explained by this direction. This is the part that is unexplained. And the measurement is always the same. The third iteration, now we have 2. Now we build A up. Again, we take this projection. Again, we remove. Go on and kind of rinse and repeat. So again, A3 will now have 3 things in it, so on and so forth. Yeah, quick question?
Yeah, I'm still kind of confused about why we're not subtracting because wouldn't that mean that in the second iteration we have more unexplained than we had in the first iteration?
Not quite, right? Because we're removing the component in both directions. So you'll see, what we're doing. But yeah. You're basically simultaneously projecting in both of these directions. Yeah? Let me check this and get back to you. The basic idea is that you subtract the components in both directions. Okay? Yeah? How can we guarantee, the question is, how can we guarantee that algorithm 2 will work? And the answer is that we can't. We're just hoping that it will work. If you take classes like 70 and then build on that, you'll learn basically properties that these different matrices have to satisfy to be able to guarantee that the algorithm will work. So in some cases, you can prove convergence of the system, and you can actually then show that under certain circumstances, the algorithm will work and will not work. But in general, this is kind of wishful thinking, because we're already trying to get more out of the system than the system is giving us. Okay, so I want to go and talk about another example for this. And in the interest of time, I'm just going to show you this kind of thing. So I want to go back to basically Module 1. And in Module 1, what did you folks do? You had an example where you did imaging, right? Single pixel camera. And what you did was you had a vector of your image, which was the unknown, And what you did was you said, well, let's take a mask and let's take a measurement, and you took that measurement, right? And you had these matrices of binary matrices that were used for measurement. And what if you knew that actually your image was a sparse image? So what if you knew that of your pixels, let's say only a few are non-zero? What can you do in this case, and can you actually use an iterative algorithm like OMP, is what I want to talk about. And hopefully this will also clarify some of the questions that are being asked. So now what we're going to do is you're going to say, if we have this setup, we're going to look at this, can you see this? This received vector y. And I want to compare this received vector y to each of these columns, C1 all the way up to C9. And remember, think about the column view of matrix multiplication. So basically, if we think about that, this first column is multiplied by A, this second column is multiplied by B, this last column is multiplied by I, right? To give us this vector. This is just a linear combination of these columns. And so if I want to figure out, well, which column is most responsible, I can just look at the correlation of the columns and the y's. And so if we do that, I actually already wrote it out so that you don't have to. But if you look at all of these correlations, if I take 2, 1, 1, 1, inner product with 1, 0, 1, 0, I get 3. The correlation of y with C2 gives me 2. The correlation of y with C3 gives me 5, so on and so forth. Right? Does everyone see what I'm doing here? And so now, if I wanted to pick out that column which most explains what we're seeing, what we're trying to do is a greedy strategy. So which is the column that I'm going to pick out? C3, right? And so what I'm going to do is then I'm going to say y minus basically the component in direction C3. And so I'm going to have y1 is equal to C3, C3 transpose C3 inverse, C3 transpose y. Okay? And so now what is my C3? My C3 is just 1, 1, 1, 1. This guy is 1, 1, 1, 1 times 1, 1 whole inverse. This is 1, 1, 1, 1. And my y is 2, 1, 1, 1. So this is equal to 1, 1, 1, 1. This is 5 over 4. Right? So the projection of my y vector in the direction C3 is given by this. So now I'm going to remove from y so my E is equal to y minus y1, which is equal to 2, 1, 1, 1 minus 5 by 4, 1, 1, 1, 1, which is equal to 3/4 minus 1/4 minus 1/4 minus 1/4. Does everyone see this? Everyone with me here? So now what am I going to do? I'm saying like, okay, I've explained part of it. So now let me do a correlation of this guy, E, with all of the guys. So 3/4 E times, or inner product with C1, so on and so forth. And again, in the interest of time, I am not going to... Actually, I'm just going to use the values that I already computed. So the correlations are half minus a half. What should be the correlation of this guy with column C3? 0, right? Because we removed that entire component. So if you look at 3/4, 1/4, 1/4, 3/4 minus 1/4, 1/4 minus 1/4 minus 1/4, and you dot product it with 1, 1, 1, 1, what you see is that you get a 0, which makes sense. You have a half, you have a minus 1/2, then you have a 3/4, you have a minus 1/4, minus 1/4, minus 1/4. Right? These are the correlations with all of the columns. So which is the column that we're now going to pick up? This is corresponding to C6. And so this means that the next matrix that we're going to compose is going to be A2, which is equal to C3, C6, and you continue. So now you have Y2 is equal to, again, A2 transpose A2 inverse, A2 times Y. And what I wanted to show you before class ended was actually this implemented. So what we have here is basically this OMP algorithm, the whole algorithm that we just described. Coded up. And this is very related to the problem that you're doing on the homework. And what this demo is showing, we have here. So let's say we have some image, and we're taking measurements of it, right? We're taking these measurements that are exactly the same kind of measurements that you took in your class, in the lab in Module 1. And generate the mass and the measurements. And then what I'm going to do is I'm going to run the OMP algorithm, which is basically exactly what we just described. Like find the column that has the maximum correlation, subtract it out. Then find the next column that has the maximum correlation, subtract out the projection onto the subspace of both of these. And let's see what it recovers. So what you're seeing down here is the iteration number of the OMP algorithm. And so it's building up one by one by one. It's saying, let me find that measurement, that column of the matrix that explains my image the most. Then it's the second best column, then the third best column, then the fourth best column. Remember, in this version, there's no shifts, right? Because it's not like you had to figure out the shift and the device. You just had to figure out that column that explains things the most in the matrix that I showed, right? And so what it's filling in one by one, it's doing this greedily. So it's finding the best thing, subtracting it out, then taking the error and doing the correlation. Again, finding the next best approximation, subtracting that out. Using the error, doing the correlation. Rinse and repeat. Question? No. Yeah?
So how can we make sure that it will keep running if we only have a certain amount of equations?
How can we be sure that it'll keep running if we have a certain amount of equations? So one thing you can do is you can just keep it running until basically you have fit all of your error. Your error goes to 0. So we didn't send our error to 0. You can keep it going until your error goes to 0. You know, sometimes that means you'll get a bunch of noise components out. Other times you might not. Our thing is still running. So it's getting slower and slower and slower. What you're seeing is that, why is it getting slower and slower and slower? Remember, doing a least squares projection involves computing A transpose A inverse, right? What is happening to A every time you run OMP? It's getting bigger and bigger and bigger. So you're doing a bigger matrix multiplication every single time. You're doing a bigger matrix inversion every single time, right? So it's more computation, which is why this is getting so much slower as we go on. Yeah, question? When we're doing the inner product of y and all of the columns, why don't we normalize? Why don't you normalize the length of the column? Or
Yeah, so we're looking for contribution, and so we're not concerned with direction.
so we are concerned with direction. So one of the reasons, this is a subtle question. So we are normalizing by the length, but we're not normalizing by the magnitude as a way of providing robustness. And in a sense, what we're doing is we're figuring out a way of removing junk measurements. So let's say you have a lot of columns that are approximately the same norm, but some that have very small norm. Like your column is 1, 1, 1, 1, 1, 2, 1, 3, 1, 1, something like that. And then you have like 0.1, 0.2, something really small. Those are probably completely junk measurements that are polluting your signal, and so you actually don't want to consider them. And so there are different kinds of trade-offs. And when you actually prove these things, you have notions that require approximately the same length or approximately the same magnitude for all of these vectors. Like this is getting a little bit beyond the scope of 16A. So if you want to have more, if you have more questions, like talk to me after class. Okay, we're almost there. 715th iteration. So the size of A is now you're inverting this like 715 times 715 matrix. And if we hadn't lost the lecture because of the class cancellation, what we'd have done next lecture is something called the Gram-Schmidt method, which actually can be used to speed up OMP. Something that you can actually, basically not have this go so slow by using orthogonalization. And so instead of doing this big matrix inversion, you can actually just find the component in the direction that you're interested in. So Gram-Schmidt is a process that basically allows you to decompose sets of vectors into sets that are where each vector is orthogonal to the other. And so you'll cover this in 16b in much more depth. Too bad we had to cancel lecture and couldn't cover it, and we didn't think it was fair to teach you new material in RRR week, which is why we decided to just schedule review lectures during RRR week. But in case you're interested in learning more about this, there's obviously notes. You can obviously come talk to me in office hours. But this is getting slower and slower and slower. It should be almost done. Not entirely sure how much time it'll take. But you can kind of see what the picture is, right? Okay, let's keep this running, and I guess in the last 5 minutes, we can keep this running in the background and just, I just wanted to, since it's the last lecture, kind of summarize where you guys have come, because it's not really just to give you a show of where we started and where we've come back to. So we started the class with this idea of, thinking about how do we, come up with the methods to design and think from an engineering perspective. And we talked very, very broadly about this kind of modeling, problem formulation, design thinking, and we covered a whole different broad array of topics. And that's probably something that's very different about this class from other classes that you've taken before. And the way I see it is that if there was one lecture or one homework problem or one discussion problem that you enjoyed in this class, I think of it as a success. We don't expect everyone to like every single problem because, there's 1,000 of you and everyone is different. But that's why there's so many different topics and so many different types of examples in the class. The hope is that, each one of you will be inspired to take at least some upper division class based on this. So there's a whole different variety of things you can go on to take. And the idea was to just give you a little bit of a hint of where you can go with your degree and where you can go with starting to study EECS. Because what you're looking at, like what this class has been, it is really just the beginning. Like, really think about what we've accomplished this class. You have built a camera from scratch. You have built 2 types of touchscreens, not just one, from scratch. And you have built essentially a mini GPS system. I definitely did not know how to do any of these 3 things when I started college. And this is in the course of 1 semester, and it's not even that you just kind of followed a pattern and matched things together, but you've built up tools by which you can explain this. So I hope, when you go home over break and visit family, maybe some of you have younger siblings or nieces and nephews or cousins, tell them what you learned. Hopefully there'll be something exciting that you can share. And lastly, I guess what I wanted to say is that, 16 will come and go, and there'll be some homework, and there'll be some problem set, and there'll be some grades. But, I hope you think about this as a marathon and not really a sprint. I know everyone is super stressed about grades. It's tough. And Berkeley does seem like this super, super competitive place. But I hope that somewhere in there, you find some little time by which you can, enjoy what you're doing. I hope somewhere you find the little bit of extra time to enjoy your homework or appreciate your homework or ask a question beyond this. So I guess if you enjoyed the class, I hope you take 16B. I hope to see you in some upper division classes. I hope that you actually think about joining course staff or, mentoring with CSM. We're always looking for people to be on course staff, so definitely reach out to your TAs or your GSIs if you're interested. And it's been a great semester. I hope you guys also thank your TAs because they have been working incredibly, incredibly hard. So with that, let's see if our Pikachu has actually finished. Pikachu is done. So this is great. So that's it. That's the end of lecture. There will be reviews next class. In case something was confusing about OMP, please come to office hours and I will hope to clarify stuff. Thanks. remember it for life.